Welcome back to the Snap tutorial series. In this video, we'll go over how to use the DAKOTA Uncertainty plugin and how to configure an uncertainty quantification analysis using a basic standpipe model. Performing an uncertainty quantification calculation using Snap requires defining the input parameters, called variates, deciding how those variates will be randomly adjusted by specifying a distribution, and finally by defining the figures of merit for the results. We'll start by describing the three main tabs that reside in the parametric properties editor within a DAKOTA uncertainty job stream. This is where the random variations are applied to model parameters. Afterwards, we'll configure the figures of merit in the report properties on the DAKOTA report job step. DAKOTA Uncertainty provides users with a comprehensive approach to quantifying and managing uncertainty in engineering analyses. DAKOTA, developed by Sandia National Laboratories, provides a robust framework for optimization and uncertainty quantification through advanced parametric analyses. It facilitates design exploration, model calibration, risk analysis, and quantification of margins and uncertainty within computational models. Knowing this, the DAKOTA uncertainty step within Snap performs the uncertainty analysis. This is a fan-in step. That is, its plot file input is a file set that reads all the connected files into a single execution. The DAKOTA uncertainty step extracts the figures of merit from the provided plot files and creates an aggregate set of extracted results in a format understood by DAKOTA. The step then executes DAKOTA in post-run mode to perform statistical analysis on the results. Finally, the report generates a Word or ODF formatted report that contains all of the information. When defining a DAKOTA uncertainty job stream, the DAKOTA configuration is edited via the parametric properties attribute of the uncertainty stream. Editing this property opens the Edit Uncertainty Configuration window, where the user is given three main tabs to configure the stream. First, we have the DAKOTA Properties tab, which implements the high-level properties for the uncertainty analysis. Here we can specify the amount of random sampling applied to the given model. The Calculate Samples button to the right of this field can be used to compute the required number of tasks for the indicated order and probability and confidence intervals according to the Wilks method. For more info on the Wilks method, navigate to Appendix A within the Snap User's Manual to learn more. If the user wants to generate a pseudo-random number of samples, they may use the random seed field to override the seed by selecting the checkbox and specifying an explicit seed. When set to a specific value, DAKOTA will generate the same sequence of values every time the stream is run. If left unset, DAKOTA will generate its own seed. In either case, the seed used is reported in the results. The sampling method specifies another constraint on random value generation. With Monte Carlo, each random variation is produced from its distribution independent of other variations. When set to Latin hypercube, the distribution is sliced into equally likely bins, and a random value is produced from each bin. The number of bins is equal to the number of samples needed. If the user activates the order value that indicates the order statistic approach is in use, the sampling method is disabled, and the Monte Carlo option is defaulted to. For more information on the order statistic method, navigate to Appendix B within the Snap User's Manual. Input error handling indicates how the uncertainty stream handles samples that cause a model to fail its model check. By default, model check errors are ignored, and the sample is used regardless. The stream can also choose to filter out any samples that produce model check errors. The third option uses the replacement factor field to create substitutes for failed samples. When using the replacement strategy for an uncertainty stream with n samples and a replacement factor of k, the stream will generate a pool of n plus k multiplied by n inputs. Inputs are taken from this pool until either n samples are selected or until the pool has been exhausted. The runtime errors option indicates how the uncertainty stream will handle samples that don't successfully complete their execution. By default, an extra 10% of models are executed and used for replacements within the DAKOTA analysis. The stream can also choose to terminate analysis when an execution failure is found. The terminates analysis selection will not submit replacement jobs, but the DAKOTA report will still be built to analyze which variable values resulted in failures. To modify the number of replacement samples at the beginning of the analysis, use the Run Replace Factor field. For example, putting 0.1 into this field would yield an extra 10% of the desired number of samples property. Finally, we have the figures of merit table. A figure of merit is a single scalar value calculated from the results of a single analysis code run. The bulk of DAKOTA uncertainty analysis is oriented around analyzing and correlating response function values across the parametric tasks, where each task represents a set of random samples. The user can define their desired amount of response functions, assign whether their response functions have an upper and lower limit, and provide a description of what the specific figure of merit represents within the execution. Next, we have the Variables tab that is responsible for defining variable definitions. This controls how the input model is varied for each set of random samples. This dialog is composed of a single table that contains buttons for addition, removal, and reordering of the variables defined. The first two columns in the table indicate the name of the variable and the probability distribution it maps to. The remaining read-only columns indicate additional values of interest pulled from the reference variable and probability distribution. When the user creates a new variable reference, a completion dialog is provided with two panels. The left panel allows the user to select a variable category and populates the right panel with the respective variables from the selected category. Notice that for trace, the variable can be a snap variable, a sensitivity coefficient, or component-specific parameters. When selecting a snap variable, only interactive variables can be used as variates for the uncertainty quantification. Once a variable is selected, the user can select the next button provided at the bottom of the dialog. Doing so will show the available properties of the new distribution. You can select or copy an existing distribution or create a new distribution with one of the three variate application rules: scalar, additive, and factor. Scalar replaces the model parameter with the result from the distribution completely. Additive takes the nominal value from the model parameter and adds the distribution value for each case. Finally, the factor option multiplies the nominal value from the model parameter by the distribution value. Finally, we have the Distributions tab. The Distributions tab is used to specify the probability distributions that define random variate generation. Each probability distribution created in the dialog corresponds to exactly one random value generated per parametric task. The distribution names and values will be assigned as the parametric keywords for each task. Selecting an item within the list on the left will display the distributions properties in the rest of the dialog, with the central area used to modify distribution properties, including the name, type, and type-specific parameters. Currently, the Uncertainty plugin supports normal, log normal, uniform, log uniform, triangular, exponential, beta, gamma, Gumbel, Frechet, Weibel, and histogram probability distributions. When creating a new distribution, the user will be prompted with a completion dialog to configure the new distribution. New distribution definitions are specified as either a factor, additive, or scalar distribution, which dictates how a generated random variate is applied to nominal values. Now that we have covered how to configure the uncertainty job stream and had an overview on the crucial properties, let's look at the report properties within the uncertainty step. These properties can be found within the report editing dialog on the uncertainty job step. We can see we have two tabs in the dialog named General and Plots. These two tabs contain configuration options for the generated uncertainty quantification report. Our first available option within the General tab is the document format. This specifies the generated report file's format and can be Microsoft Word or the Open Document format. The title page allows selecting a model note that will be used as the first page shown in the report. Similarly, the note selected for the front matter property will be displayed after the title page and table of contents. Both properties have three buttons that can select a pre-existing note, an edit button to edit a currently selected note, and a preview button to generate and display the note in the format specified by the document format. The optional header and footer text provide text labels to display at the top and bottom of each page in the document, excluding the title page. The miscellaneous section provides various types of features for the report like section titles, random variates generated for the uncertainty run, inclusion of the figure of merit values that can be sorted in different ways, inclusion of the extract script defined within the property view of the DAKOTA uncertainty step and input file, as well as adding page numbers in a table of contents. Next, we have the Plots tab that can be used to include plots of figures of merit or random variate samples. Plots can be added, removed, and reordered within the report by using the toolbar provided on the left panel of the dialog. Here, the user can view and configure each of their defined plots using the left panel's list to select a plot. Clicking on a plot will populate the property view of the dialog with its attributes that the user will define to identify and configure each plot's various properties. Each plot comes with three main attribute groups. The general attribute group contains properties for defining the title and subtitle of a plot, a plot type attribute to define the type of plot used, a plot option that chooses whether the plot shows one or more variate values against a figure of merit, or one or more figure of merits against a single variate, a y-axis value that defines a dependent variable for the respective plot, a variables editor that includes variables defined in the model with this plot, and finally a trimmed outliers option that defines a number of values to remove from the upper and lower bounds of dependent variable values. Keep in mind that this will apply to all data sets. After the general attribute group, we have the X and Y axis properties that define properties like axis labels, modes, bounds, and scales. Setting the mode to fixed for either the X or Y axis will enable the axis bounds property. When enabled, the values set within the text field for these properties must follow the bracket convention seen in the dialog, where the lower and upper bounds are wrapped within a pair of brackets and separated by a comma. Now that we have covered the layout of the two crucial dialogues, let's begin our example of creating a DAKOTA uncertainty stream. Open the model named Uncertainty example included with the link in the description of this video. Once opened, navigate to the Job Streams category and create a new job stream. For this example, select the DAKOTA uncertainty option and click Next. We'll use a trace restart stream that will provide us with a steady state and transient stream step. Our transient XTV file will feed into our uncertainty stream to model the behavior of plot channels within our model. Name the stream UQ stream and open the parametric properties editor to update the uncertainty configuration. We'll start by creating a new figure of merit using the table provided and name the new entry as temp. Once created, navigate to the Variables tab and select the heat flux variable defined within user-defined reals. Notice within our right panel that we have three values that are grayed out. These values are not interactive variables and therefore cannot be used within the Variables tab for the uncertainty stream. Click Next and select Factor from the available properties for the new distribution. Click Finish and navigate to the Distributions tab and rename the defined distribution as heat flux. Change the standard deviation to 0.03. Once we have set up our distribution correctly, navigate back to the DAKOTA properties and click the Calculate button for the number of samples to auto-generate the correct number of cases we need for the uncertainty stream. For our example, we'll ignore model check errors, and we'll replace incomplete/failed runs. With our run replace factor set to 0.1, we will generate 10% more cases than what is needed based on the number of samples provided above. Now press OK. We have now configured our uncertainty stream properly. Using the Restart Stream tab provided in the Views window, click on the base model and flag the model as a parametric stream. Now navigate back to the UQ stream we defined and create a new uncertainty step. Set the plot file type to trace and set the response time to 180 seconds. You'll notice that with the Use Custom Extract step set to false, we now have the option to see our response figure of merit we defined earlier within the property view. Open this editor and place the following text into the plot channel. This will represent plot data from channels defined within the model that we will obtain from the trace transient run. Now open the report dialog, set title page to title page, and click on the Plots tab provided in the dialog. Create a new plot and set the y-axis value to the figure of merit we previously defined. After setting the figure of merit, edit the variables property and add the heat flux variable we previously defined in the parametric properties editor and exit the report dialog. Finally, drag the uncertainty step into the restart case view and using the connection tool, connect the trace XTV file to the input labeled plot on the uncertainty step. Congratulations! We have set our uncertainty stream up in its entirety. Now let's submit it to the local calculation server and view our results. Once the submission has been executed successfully, you can see the results within the job console. Click on the UQ_stream within your currently completed jobs and click on the step option at the bottom of the completed steps. After you've done this, you can view your available report generated by the run by clicking the View Available Job Files button and selecting the UQ_report file within the Documents option. The Uncertainty Quantification Input Options section provides a summarization of the analysis. The first few entries specify the current versioning of Snap, the Uncertainty plugin, and the current plugin that DAKOTA is being used with, as well as the model name and location. In addition to versioning and model information, this section also includes the properties we used within the DAKOTA Properties tab, as well as identifying the total number of tasks executed, the number of allocated tasks for errors, and the total number of successful tasks during the run. Finally, this section provides us with synopsis of the model variables and distributions defined within the parametric properties dialog, as well as some application information used within the job submission. Next, we have the figures of merit section that shows the response functions that we defined within the model and were used during the uncertainty quantification. After the figures of merit, we have the variate and response data section responsible for showing the submissions values for each task in a tabulated format. Errors that occur during the run will be at the top of the table and will be highlighted in red. Finally, at the bottom of the report, we have the DAKOTA results and input file. This group shows a couple of graphs showing a cumulative distribution function and probability density function for the figure of merit we had defined earlier. It also contains a table that has some statistical results from the submission and a small input file that was used in a pre-run DAKOTA invocation to generate the random variates.